Hi, let's begin with lecture 3. I'm just going to show how to use the software Aspen HYSYS. So to open the software, all you need to do is, if you want, you can type HYSYS, then just click Aspen HYSYS. I think in our university, we will have version 10, so just click on it. You'll get some warning. Just close this window. So let it open. So you can press cancel all these things. Cancel. Press cancel. So to start the new project, just press new. So that's how your window will look like. Hope you all can see this clearly. You have something file, home, view, customize, and resources. And by default, you will have this Aspen HYSYS will show this page to you. Then you will have something on the left hand side like a component list, fluid package, something like a petroleum assays, reactions, and so on. Then in the below you will have like a properties and then simulation. So this will also give you some idea where to begin. Yeah? So probably we have to begin with this one, component list. So it's already opened here. If you see here, you will see the tab component list, which is already open. And then the second one should be fluid package, and then third one will be any of these points which are listed here. And then we will go on to simulations and so on. So if you were listening to this, which is lecture 3, without listening to lecture 1 and 2, probably you will have no clue, yeah, what's happening. So I recommend you to first watch lecture 1 and then lecture 2. Yeah? So you must watch both lecture 1 and lecture 2. I think lecture 2 I splitted the videos into 2 or 3, I think. So it will be part A, part B, and part C. So you must watch all the 3 parts, and only then you should come here. Yeah? So if not, it will be very difficult for you to understand. Yeah? So in lecture 2, I clearly explained how to manufacture vinyl chloride monomer and what are the reactions involved and so on. So you have to, and also the process conditions. Sorry, so you must listen to lecture 2 before coming here. Then we also made a small PowerPoint to show you before we begin. So this is like a quick summary. If you see here, we have so we have 3 different chemical reactions involved during the manufacturing of vinyl chloride monomer. And then in terms of chemicals involved, you have okay, just if you consider reactants, you have ethylene, you have chlorine, you have hydrochloric acid, and then some oxygen. And then in terms of products, you have ethylene dichloride, we have water, and then finally the vinyl chloride monomer. So before starting Aspen HYSYS, you should have this list. So what are the different chemicals involved, or just the you have to know the chemical formula of both your reactants and also your products involved in all the chemical reactions involved in the process. So in this case, for the manufacturing of vinyl chloride monomer, we have mm, few reactants and then few products. So if you count them in total, so ethylene is 1, chlorine is 2, ethylene dichloride is 3, water is 4, oxygen is 5, hydrochloric acid is 6, and then vinyl chloride monomer is 7. So you have 7 fluids. So you have to remember this. First we will add add this fluid in the software. So when you're going to work with Aspen HYSYS, the first thing that we have to do is add the different fluids involved in the whole process. Yeah? So let's go back to Aspen HYSYS. So let's add. We're adding the different fluids, and here you can see like search by full name or synonym, or we can also search by formula. So I'm going to search by formula because it will make our life a bit more easy. So let's do that. So it will be C2 ethylene. Let's load ethylene C2H4. So you will have ethylene here. So just double click on it. So it will, okay, you have ethylene here. Just double click. So it will come to the left side. You see the left hand side component and type. It's a pure component and it just pure ethylene. We loaded already. And then let's load Cl2 chlorine, which is here. Just double click. So we added one more pure component. So whatever we are seeing now, so this is the procedure to use Aspen HYSYS. We open the software and then the first thing that we need to do is some fluid components. Yeah? So if you have any process or even just a small unit operation, say like we are mixing A plus B in a CSTR, then we have to load component A and component B. And then we also have to load whatever the products. If we label it C, then we have to add the component C. So we need to add our fluid component. So this is the first step in Aspen HYSYS. So what we're going to do now is like we will develop the full plant for the vinyl chloride monomer production, but at the same time we are also learning how to use the software and what should be done and which should be the first step, and then once you add the fluid, what should be the next step, and so on. So there are some procedures that we have to follow. That's how the software will work. So just to follow this procedure, so if you do this exercise from top to bottom, then probably you will get a bit level of proficiency with the Aspen HYSYS. You will see a lot of error when we are going to solve this. And I learned, I have to confess that I learned Aspen HYSYS through by watching a lot of videos in YouTube and so on. But whenever I watched YouTube, it's always like they start the exercise and they finish the exercise and everything works fine. There will be zero error encountered. So seems like they can manage to work with Aspen HYSYS without encountering a single problem. Yeah, but this is not the case. So when you start to work by yourself using Aspen HYSYS, you will see a lot of error messages, and if you have chemical engineering knowledge, then you will fix it. Yeah, so obviously we shouldn't be scared of those errors, and once you fix the error, it will give you more and more confidence, and you will get even more and more familiarized with Aspen HYSYS. Yeah, so don't be scared like when if you get some error messages or so on. Yeah? So just to think what could be the error message, or how what could be the problem. Yeah? So think and then fix the problem. So if you manage to fix the problem, it will be really rewarding. Yeah. So you will realize that okay, you managed to solve some problem by yourself. Yeah. So that's a big thing, as a chemical engineer. So so what I'm going to do is like I will show you how to use the software, how to deal with this particular case, which is production of a vinyl chloride monomer. And then if I will edit this video because I cannot talk forever. Yeah, like for 4 hours or 5 hours. So I will take some break for myself. So I will pause the recording and then I will continue again. Obviously, once I finish the whole exercise, I will split it into 3 or 4 sessions so that so depending on how fast I am going at this moment and how many error message I'm going to encounter while developing this project. Yeah. So also I want to say like if there is an error message, I'm not going to edit and remove those sections. I'm going to leave those error messages and I'm going to talk to myself like how I'm going to fix this error, what I think the error could or what I think about the error, or why something is something like it displays, you see here green, you will get something like a red color flag here. So we will think like why I see something like that. So i will I will talk while recording so that it will give you some idea like how to fix those errors, and probably you might encounter something similar while you are developing your project. So let's continue with this exercise. So I already added ethylene, already added chlorine, and then we have to add ethylene dichloride. The formula is C2H4Cl2, ethylene chloride, blah blah blah. There it is. C2H4Cl2. Okay, just a double click. We already added here, and then hydrochloric acid is one of our reactant. So double click. We have hydrochloric acid. We need this for oxychlorination reaction. Then we can add our main product, which is vinyl chloride monomer C2H3Cl. So it should be vinyl chloride monomer. Just a double click, so it will be added to the left hand side. So we have ethylene, we have chlorine, we have ethylene dichloride. We need water, which is one of the product in oxychlorination reaction. Water we added already, and then instead of oxygen we can supply air, because the air contains significant amount of oxygen. Yeah, that's why we are surviving at the moment. So let's put air. Okay, we can put full name. Okay, just type air and then you can double click. So we have 7 components: ethylene, chlorine, ethylene dichloride, hydrochloric acid, vinyl chloride monomer, water, and air. Yeah? So we already added all the fluids. So we call them as if you want we can call like a fluid components, or just simply component list. We have the all the reactants and products involved in all the chemical reactions during the manufacturing of vinyl chloride monomer. So far good. So what to do next? And then the next step is we need to add a suitable fluid package. So what is this fluid package is about? So we need to define the fluid properties here. So if you put the correct fluid package, it will accurately predict the fluid properties. Yeah, say like the fluid package will take care of the properties of the fluids which we added in the component. Say like if you give temperature is 100 degrees centigrade or above 100 degrees centigrade, it will show some water in the vapor phase, and then if you put temperature of say like say 5 degrees centigrade, it will automatically predict water is in the liquid phase and so on. Yeah? So it accurately predict the fluid properties, something like an equation of state. In fact, we will have some equation of state. Wait a second, let me check my notes one time. I think everything looks fine. 2, 3, 4, 5, 6, 7, and then we can add fluid package. So if you click add, I don't know whether you can see the screen clearly or not. I have to check once. When I'm going to edit, I will check how clear the screen is. So for this particular problem, we are going to use PRSV fluid package. And if it's a green means which is everything is okay, and this particular fluid package includes all the fluid properties of the 7 components which is already added here. So this is like a I can write for you. What is this about? So what we added is Peng Robinson. I hope you all know what is the Peng Robinson equation of state. Strayak Vera fluid package. So that's the fluid package we're using. So the first step is we have to add the components, and then we have to select the correct fluid package have that will that will predict accurately the fluid properties of all the components involved in this particular chemical reactions or in the series of chemical reactions. So, so once you select this fluid package, you will see something green. So there is some advantage with this software Aspen HYSYS. So if you do a mistake, it will say something is not correct. If everything is fine, then it will show you like a green signal. Say for example, if you select something like some other thing, it will say this is not a recommended package, and it says it cannot find the fluid properties for the chlorine atoms. So, but anyway, Penn-Robinson equation of state is good for most of the gases and so on, especially small molecules. So select this one, and then we can also use Penn-Robinson equation of state, but I'm going to use this one, PRSV. This is recommended in some of the books which I follow. So click this one. So once you finished this, and then if we go back to the slides, so we have three chemical reactions. One is direct chlorination, another one is oxychlorination, and third one is pyrolysis. Yeah. So and the lecture two I already said to you the the rate of reaction for each of these chemical reactions. So I will bring it. If you don't remember, I don't know whether I have a copy here. Check. This is the notes from lecture 3, I think. So so that's the rate of reaction for the mhm. No, this is for the pyrolysis. Okay, let me check my notes here. Yeah, so for the direct chlorination reaction, I took the, the rate expression from this paper, Hokim Orejas from it was published in Chemical Engineering Science. So that's the direct chlorination reaction. And then the rate expression is given by kinetic constant multiplied by concentration of ethylene multiplied by concentration of chlorine. And then where the rate constant is given by here, K is equal to 11493 exponential of your activation energy divided by T meter cube kilomoles per second. So if you so this value is activation energy divided by R. So how to write here. So this 21563. Try to write. So 21563. Sorry, 2156.58. So this is nothing but E by R. So therefore, E will be equal to 2156.58 multiplied by 8.314. So joules per mole. So that will be your activation energy. I think that will be, I already showed this in the previous lectures. So this should be equal to 179, sorry, 17929.81. That will be your activation energy. So your K will be equal to this big number which is here. Sorry, this value exponential of minus this value 17929.81 divided by RT divided by RT. So that value will go here, replace here. And then you have the R value, the K value, sorry, the kinetic constant is expressed in terms of meter cube per kilomole per second. So keep these things in the mind, and we are ignoring this reaction at the moment in this particular project. So let's go back to the Aspen HYSYS software. So I'm going to go a bit slow, yeah, because it's very tough, believe me, and you should know how to deal with these things. So let's see this. Check the time. It's spent already 22 minutes without doing anything. So let's do that. So what we need to do now, we already added the fluid package. We're happy with this PRSV, and then we have to go to the reactions. So we have three chemical reactions. So that's the procedure in Aspen HYSYS. The first one, we added the components, and the next one is we added a fluid package, and then we are going to add the chemical reactions. So let's add the first thing, which is what? Which is the direct chlorination reaction. So let's click add reaction, and this is a kinetic reaction. So it is first order kinetic specific. So click kinetics and then press add reaction. So once you added the reaction, just close this, just double click. You put your mouse on the reaction one, just double click. So double click, and then it will ask you add the components. So what are the components involved in the direct chlorination reaction? So let's go back to the PowerPoint. So if you come back here, so these are the components in the direct chlorination reaction: ethylene plus chlorine, and then which give rise to ethylene dichloride. So we have to add that. So let's add. So let's add ethylene, chlorine, and then what's that? Ethylene dichloride. And then we have to mention the stoichiometric coefficient. If you go back to our PowerPoint, you will see 1 mole of ethylene, 1 mole of chlorine, 1 mole of ethylene dichloride. So 1, 1, 1. So go back to Aspen HYSYS. So stoichiometric coefficient, which is 1, ethylene, chlorine is 1, and then this one is minus 1. So what does this minus 1 mean? So plus 1 and plus 1, which means they are reactants, and minus 1, which means it's a product. So, and then the reaction follows a first order kinetics with respect to ethylene. So first order kinetics with respect to ethylene, and then the remaining will be 0. So I think so far good. I'll just check the notes because I don't want to do any mistake. So this, whenever I say notes, this is nothing but the key sheet which I ask you to generate. If you listen to lecture 3, in the last 10 minutes, I asked you to listen to the lecture fully and then generate a key sheet. So that's what I'm checking at the moment. So everything is fine. And then I think the reaction is with first order with is K concentration of ethylene. Go back to that PowerPoint. So first order with respect to ethylene and also with respect to chlorine. So just to follow the cursor here. K C A C B. So it should be first order with respect to chlorine. So this is fine. And then you see here something like a red color. Something is highlighted in the red, and then if you can read this, it says it's not ready. Yeah? So what's missing here? What's missing here is we have to mention the pre-exponential factor, or if we can call it as a frequency factor, activation energy, and so on. Yeah? So let's enter the pre-exponential factor. We already have this value. If we go back here, it's 11493, 11493, and then activation energy is something we calculated here, 17929.81. 17929.81. This value should be correct. If not, everything will be wrong. And then base component is so this is something I'm going to select. It's not allowing to select me. Select. Let me check what's the problem. No, I did a mistake. Okay, I know what's the problem. So the problem is reactant should be minus 1, and then product should be positive 1. Okay, so this is perfect. So so stoichiometric coefficient is correct. I put the sign wrongly, so that's why I'm going to record everything, all the mistakes that I'm making. Obviously, you are going to make the same mistake. So nobody is expert here. You all are learning, you and me. So minus 1, and plus 1. And now we can select the base component. Before I, I was a bit puzzled because the base component should be always your reactant. So what I'm going to select is ethylene. So what this base component mean is like the percentage of the product which you're going to see on the right hand side of your expression, that depends on how much of your this base component is converted. So something like ethylene will be the limiting reactant. And anyway, if you remember, that's why I asked you to generate the key sheet in the lecture 2. So I already said we are going to supply chlorine in excess to that of the stoichiometric amount. Okay. So far everything looks fine, and then it's also say everything is ready, green and ready. So which means Aspen HYSYS is happy with whatever we did. So this is perfect. And if you see here, you also have like a forward reaction, something on the reverse reaction. So this one we don't have to fill anything at the moment because our reaction is it's a simple first order kinetics with respect to both ethylene and your chlorine. Yeah? So we will come back to this reverse reaction and so on. So what we do is like let's finish this full project. This will be really time consuming, believe me. And once we finish this, so I will try to I will generate some complex chemical reactions with some funny rate expressions, and then we will try to see how to implement in the Aspen HYSYS. So that thing we can learn it separately. For the moment, just stick to do this one. So at the moment, you know how to add a first order reaction in the Aspen HYSYS. You know to add fluid components, select a suitable fluid package, and so on. So this is okay. So let's close this reaction phase. I think let's put overall. So it will be, it will consider both liquid and gas phase. So let's close this one and then add reaction. So the next one in the plug flow reactor. So let's go back to this our presentation slide. So if we go back to slide, oxychlorination, we are going to perform this in a plug flow reactor and using a catalyst. And I said to you like this particular the rate the rate of reaction is given by a Langmuir Hinchelwood kinetics. I already copy pasted some information from the literature for you. Anyway, we already covered this in lecture 2. But, so this is the manuscript I was talking about. It was published by Vachi and Asai in some Japanese group. It was published in 1994. So that's our oxychlorination reaction. And they found that they performed this reaction in presence of a catalyst, CuCl2 catalyst, and they found the rate of reaction follows the Langmuir-Hinchelwood expression given by here. Kr is your rate constant, Ka is absorption constant, Ca is a concentration of ethylene, this one is a concentration of chlorine atoms in the catalyst, and then Ka again is a absorption constant. So I think this one looks fine to me. Multiplied by concentration of ethylene, there is some printing mistake. So C suffix E. Yeah. And then Kr is given by 269. So this is expressed in terms of what? Kr is expressed in terms of 1 by second. So that's perfect. And this one is expressed in kilojoules. So we have to convert it into joules. So when we enter into the Aspen HYSYS software, and Ka is expressed in terms of meter cubes per mole. So it will be 630 meter cube per kilomole. So how it will look like, I will try to write it for you one time to make the. So if you plug in here, your rate expression will look like. So my handwriting is not really good. We'll try to write a bit slow. Multiplied by Ka value is 630. Ka value is 630 a meter cube per kilomole, and then exponential of minus 37800 by RT. I think this is fine. So divided by 1 plus 630 concentration of ethylene, the numerator concentration of ethylene, concentration of Cl2 chlorine atom. If you see into if you look into the lecture notes, I already said this is equal to. They already calculated the concentration of chlorine atoms in the catalyst, so that will be equal to 0.993 kilomole per meter cube. So we already know the concentration of Cl2. This is a constant because this is the concentration of chlorine atoms in the catalyst, so which is a constant number. So we can multiply 0.993 multiplied by 630 multiplied by 269. So you will get something like, I will write it in the top of the PowerPoint. So R will become 168284 concentration of ethylene exponential of minus 37800. Sorry for the poor handwriting. First of all, my handwriting is bad, and it's even very difficult to write using the very cheapest pen which I'm using at the moment. 630 ethylene, and then I think that's correct concentration of ethylene. So this is the rate expression that we need to add in the Aspen HYSYS. So let's try to add. So this is your K value, concentration of ethylene, exponential of 37800 by RT. Okay, this is a Langmuir-Hinchelwood expression. This is a heterogeneous catalytic reaction. So this is something good. I don't have to repeat this, but you could probably you should have this already in your key sheets. So, but anyway, I will just go with slow by slow because it's a really a heavy duty project, and you need this type of knowledge, especially when you go to, especially for when you are going to deal with a design project in your final year. So it's okay to go a bit slow. So let's come back to Aspen HYSYS. So that will be heterogeneous catalytic reaction. Press add reaction. So just double click. Okay, close this window. So now this is reaction 2 is a heterogeneous catalytic reaction. You can see RxN2 type is heterogeneous catalytic. So double click on it. So obviously the rule is same. So for reaction 2, again we have to add the components. If you go back to the PowerPoint slide, so if you look at here, oxychlorination. So these are the components: ethylene, hydrochloric acid, instead of okay oxygen, and then what is this? This one is ethylene dichloride plus water. So we have to add 1, 2, 3, 4, and 5. And then you have to pay attention to the stoichiometry. 1 mole of ethylene, 2 mole of hydrochloric acid, half a mole of oxygen give rise to 1 mole of ethylene dichloride and 1 mole of water. So keep those things in the mind. So go back to the Aspen HYSYS. So let's add ethylene first. So ethylene. So don't rush when you are going to do. Then you will end up with some mistake, and then you have to scratch your head. So better go bit slow, ethylene, and then your hydrochloric acid, your reactant, and then we can add. This is tricky now. No, instead of air, let's add because we have oxygen in the reactants. So let me close this one. So let's go back to component list. Let's click air and then remove. Anyway, we know the composition of air, so let's add oxygen first. Oxygen. Obviously, air contains nitrogen, so let's add nitrogen as well. So what we are going to do is in the process, instead of buying pure oxygen, we are going to just supply air for the oxychlorination reaction because air itself contains oxygen, 79% of oxygen. So double click nitrogen. So again, come to fluid package. Everything is fine. Then come back to reaction set. So just double click on reaction. Now we can add oxygen here. Select oxygen, and then in the product side, so this is something you learned. So if you have oxygen molecule, you have to select oxygen in the component fluid component list. What else we have in the oxychlorination reaction? We have ethylene dichloride and water. Ethylene dichloride, and then we have water. And then now you remember the stoichiometric coefficient. Yeah? So minus, so 1 mole of ethylene, 2 moles of hydrochloric acid, half a mole of oxygen give rise to 1 mole of ethylene dichloride and 1 mole of water. Oh, and then pay attention to the units. Even before I forgot to mention. So at the moment the units is in terms of kilomoles per meter cube, kilomoles per meter cube, and if we go back here, if we come down, we have, that's why we converted our units to rate is expressed in terms of mole per seconds per meter cube. So we have to convert this into kilomoles per second per meter cube. Yeah? So we already did that. That's why we converted this value. What is that? 0.63 converted into meter cube per kilomole. That will be 630, and then this value 993. This was okay. They reported if you go into the original paper, I think they reported something like 993 something moles per meter cube. So I converted it into 0.993 kilomoles per meter cube. So if you read this full paper, you will see this number somewhere. Yeah, concentration of chlorine atom in the catalyst. So I converted already the reaction rate of reaction into kilomoles per meter cube per second. So you don't have to worry about this. So this is the correct number. If you enter this number, then automatically your rate will be expressed in terms of kilomoles per second per meter cube. So let's enter this value, the frequency factor, 168284. So go back to our, so we already have the stoichiometry, everything is perfect. Go to reaction rate, and here you have to mention forward reaction. So what's the value? I said to you, let me open my case sheets. So it should be 168284. So that's why I said before the lecture 2, I advised you a million times. Like you have to be clear what type of about the activation energy and so on, and you have to use pen and paper a lot, yeah, before using the Aspen HYSYS. Aspen HYSYS is only a software, but Aspen HYSYS itself is not a chemical engineer. You are the chemical engineer, so it's your job to make sure the things are correct. Then the activation energy is 37800. And one more thing I forgot to mention. So activation energy, if you go to the PowerPoint, you have this minus 37 minus 37800. So you don't have to put the negative symbol. Yeah? By default, in Aspen HYSYS, it's minus sign. So by default, it follows the Arrhenius rate law. Yeah? So 37800. Then everything looks fine. And then the reaction is stoichiometry is perfect. And again, go to stoichiometry, and then again, base component is ethylene, and then reaction phase again is overall. So it will take whether no matter if you have these components in liquid or gas phase, it will react following the particular rate expression. So this is a forward reaction. Everything looks fine to me, and then the process is first order with respect to ethylene is first order with is only with respect to ethylene. So you make these things zero. So you have to pay attention. Yeah, Aspen HYSYS is crazy sometimes. So it will put some value for some reason based on the stoichiometric coefficient. It will think, oh, it's second order with respect to ethylene dichloride and water, which is not true. So it's only first order with respect to ethylene. And then if you go back to that expression, Langmuir-Hinschel expression, so your kinetic rate expression doesn't stop here. So K something multiplied by this value exponential. You also have something in the denominator, which is 630 with respect to ethylene. So by default, you will have this 1 plus, you have to write the denominator components. So 630 multiplied by concentration of your ethylene. How do you write that? So just to pay attention, 630 multiplied by concentration of ethylene. So that's how you deal with, you write in the you enter the formula. So you see the word here, denominator. So and you have to write the energy value is 630 630 630 with respect to 630 with respect to ethylene. Yeah, because 630 multiplied by ethylene. So just put 1 here and then put everything else 0. So you see here everything turned green, so which means we already entered the Langmuir-Hinshelwood expression. So this is for reaction 2, heterogeneous catalytic reaction. So that dictates the how the reaction proceeds during the oxychlorination reaction. So this part is perfect. So let's close this one. So one thing I have to tell to you again and again, you have to pay attention to the units. So if you are using grams per mole per meter cube, then these values will change. A and E value will be same, but A value will change. Yeah? So E is always expressed in joules per mole. So 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 pay attention to these things. Yeah? So 37800. It says kilojoules per kg mole, or it's joules per mole. Both are same. Yeah? So joules per gram mole, kilojoules per kilogram mole, both are same. So units are perfect. So let's close this, and then we have one more reaction to go. Third reaction is your pyrolysis reaction. So that is a simple first order kinetics. Let's open my notes here. This one we covered in the lecture 2, I think. Yes. So I said the pyrolysis chamber, the rate expression follows the first order kinetics. R is equal to K multiplied by concentration of ethylene dichloride. And I took this from the journal Computers and Chemical Engineering, volume 23, 1999, 479 to 495. So we have a if you are in the university, you can easily download this article, or if you're connected to your wireless with ED-ROM, it will also allow you to download this article, and then you can see this particular expression. Yeah? So we are going to use this expression. This is a simple first order kinetics with respect to concentration of your ethylene dichloride. And if you go back to our presentation slide here, so ethylene dichloride pyrolysis, this is our third step. So you see here three components: ethylene dichloride, and then your product vinyl chloride monomer and hydrochloric acid. Again, look at the stoichiometry. So 2 moles of your ethylene dichloride, 2 moles of vinyl chloride monomer, 2 moles of hydrochloric acid. So let's minimize this, and then let's go to our Aspen HYSYS. So this is a simple first order kinetics. So just put a kinetic reaction, add reaction. So we already added, close it. So now we can double click on the reaction 3. So we have to add all the reactions now, yeah, before going into the developing the flow sheet. So this is something you have to remember. We have to add the fluid components, select a suitable fluid package. And then once we're happy with the fluid package, then we have to think what's the different chemical reactions involved, and then we have to add those reactions. And obviously, you cannot just add the reaction. You should have other fine details like about the rate of the reaction. Obviously, it's connected to your activation energy, whether it's a first order, is it a catalytic reaction, or what type of expression we need. Yeah? Even we can use a complex rate expression, and we can plug it into Aspen HYSYS. So I will teach you separately. For the moment, just follow this particular process. Yeah. So let's add the components. Ethylene dichloride, Mhm. and then it's going to release vinyl chloride monomer. Oh, let's check the and then hydrochloric acid. Okay, and stoichiometric coefficient is -2 +2 +2. So check one time in the -2 +2 +2. Everything looks good to me. And then the base component is ethylene dichloride. That's correct. Let's put overall. And then this first order kinetics. And then I think I have the I don't remember exactly. K value here. K is okay. This value 1.14 into 10 to the power of 14. Okay. So 1.14 into 10 to the power of 14. It's correct. Let's check. then 242672 by RT. 242672. That's our activation energy. 672. It's a massive energy. So green, ready, all good. So we should be happy now for the moment. Still something is saying, you see some yellow reactions, warning. Don't get scared. It says it's not attached to the fluid package. So we can click reaction 1, press add to fluid package, press and then add set to the fluid package. Yes, we already added all of them. So the set is, we have one set with 3 different chemical reactions and we added the whole set to the fluid package. And now everything should be green and it should be ready for the next step. So I think this is so far good. We already added the components, we already added the fluid package, and then we already added the reaction set. So we have 3 reaction, 2 first order kinetics, and 1 follows the Langmuir-Hinshelwood kinetics. First one is the direct chlorination, second one RX and 2 or reaction 2 is the oxychlorination step, and then third one is the pyrolysis of ethylene dichloride to vinyl chloride monomer. Yeah? So then everything is fine, and this is the main step. We are going now to the simulation. This is the place where we are going to add the develop the full process flow sheet. Yeah? So I will just show quickly the how what we are going like how the interface looks like. So you have something called as a model palette. So if you these are the things, different operations that we are going to perform. Something like mixer. Some if you need to mix 2 or 3 fluids, then we will use mixture. Or if you want to split one fluid into say like we have one single stream and then we wanted to split it into 2 or 3 streams. So we can use a T joint or T splitter. I don't know how to call. Then we have heater, obviously cooler, and then many unit operations. Almost every unit operations involved in chemical engineering. Heat exchanger, pump, mhm, like a 3-phase separator, and then normal tank, and then compressor, expander. Obviously, we will have it's a chemical engineering software. Yeah, so we will have distillation column. We also will have absorption column, like a component splitter, pipe segments, everything that you can name. And then can also perform some special operations like, okay, now, like if I ask you to calculate, adjust the volume with respect to residence time or adjust the residence time with respect to volume, then we need to use something called as a spreadsheet. This is something like a Microsoft Excel. And then you can add formulas like something we do it in Microsoft Excel. And I don't know if you know how to use a solver add-in in Microsoft Excel. If you know that we can do something similar in Aspen HYSYS using this spreadsheet followed by adjust function. So, but anyway, I will show you how to do this. Yeah, because I selected this particular project for a reason. It has most of the major unit operation, most of the minor unit operation, and then you can. I will also show you how to do this. Use this spreadsheet and adjust and optimize the, the parameters. Yeah? So if you don't know what's the volume of my reactor, but I know the residence time um, in order to achieve some particular conversion, say like 90% conversion can be achieved if my residence time is say like 1 hour, then what could be the volume? And if I know the flow rate of my reactants that should enter the reactor, then from that I can calculate the volume. I will show you how to do all these things, yeah, while developing the process flow sheet. And then these are other things like fired heater. You can name it. We can do many things. Yes, a normal continuous stir tank reactor, which we are going to use anyway. Equilibrium reactor, Gibbs reactor, and so on. So normally Aspen HYSYS is a massive software, yeah, and it's not a bad idea if you start to or if you are introduced to this software from your year 1, yeah? But for some reason we are learning it at year 3, which is not bad because now you already know you learned the theoretical concepts of like like how distillation works, how absorption column works, how do you define a residence time, how do you calculate the residence time, and you know what is a dilution rate, and so on. So if you know these things, then we can use the theoretical knowledge to implement in Aspen HYSYS. Yeah? So those things you will learn. So I will show this full project for you bit by bit, very slowly, and you are going to do it with me. You have to play the video, pause the video, go to the next step, play the video, pause the video, do the next step, and that's how it works. That's how you are going to learn. And once you finish this, I will do some tough examples, especially how to add a heavy duty chemical reaction into Aspen HYSYS and so on. And then I will give you some some exercise. It's not exercise. It's a simple book. Follow the book, and then you can learn something by yourself. Yeah. So Aspen HYSYS is this is not something like I teach. Okay, blah 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 is defined as blah blah blah, you you try to understand, take the notes, and then come back and solve the problem. No, it doesn't work like that. Yeah, something I teach you, something you follow, and something you practice, and then something you learn by yourself. So that's how it works. So why everybody is so familiar with the Windows operating system? Because we use it every day, and that's why we are so familiarized to that particular operating system. Yeah? So that's the main that's the easiest way to learn this software. Yeah? So, anyways, I will stop giving advice. I will go what will tell what to do next. And forgot to mention there is something very important. This is material stream. Some stream that goes inside, some stream that comes out in the process flow sheet. Yeah. So this is the some streams that we will. And then this is an energy stream. This is a component stream or a material stream. So let's begin. Let's begin with our project. Huh? So we said, let's go back here. So everything begins with your direct chlorination reaction. So we have ethylene and chlorine here. This is the notes which I was teaching you in lecture 2. I don't know, part C, I think. I don't remember, but it's in general lecture 2. So ethylene plus chlorine reacts at say at 60 degrees centigrade. We call it as a low temperature chlorination. If you remember, I'm going to use a CSTR to mix them, and obviously this is carried out in presence of catalyst. But since we have the rate of the reaction added, whatever that goes inside, it will proceed at the rate of the catalytic reaction, because we already defined the activation energy and so on. And then we take some product out, and then again we are going to use the same ethylene, and then we are going to add hydrochloric acid, and then we will get some product. So keep these things in the mind. So we have to add a few streams, which is chlorine, ethylene, hydrochloric acid for this particular two chemical reactions. So at the moment we are going to take care of these two processes, which is follow the cursor, direct chlorination, and then oxychlorination. This is what we are going to do. So we have to add these reactants: ethylene, chlorine, hydrochloric acid, and then oxygen. We are going to use air. Air contains a lot of oxygen, so let's supply air in excess. So let's do this. Um, let's minimize this. Go to the so the first thing we have to add is material stream. So let's add chlorine atom. Sorry, chlorine molecule. So so what is this composition? Click the composition. Let's add chlorine. Click chlorine and then press 1. If you press 1, it will automatically adjust everything to 0. You can press OK. So it will automatically put everything 0. Or if you don't like, you can just click 0, and then you can manually enter 0, 1, 0, 0, 0. So what does this mean? Like, we have some material stream and it contains only chlorine. So chlorine flows into that particular stream. Obviously, we are not defining the flow rate at the moment. At the moment, we are just defining the composition. which is 1 pure chlorine, and it contains 0% of other components. Okay, and then let's go to conditions. Okay, if you click here, it will says that, oh, I don't know the temperature. That's what it says, unknown temperature. Yeah? And if we go back to our chemical reaction, so we are going to perform direct chlorination at this is low temperature chlorination conditions, 60 degrees centigrade, and at a pressure of 1.5 atmosphere, slightly above the atmospheric pressure. So, and if you remember, I said it in the lecture 2, this is below the boiling point of ethylene dichloride. So we are supplying 2 gaseous products, and then we are going to get 1 liquid product. So let's go to the yes, Aspen HYSYS. So let's put the temperature 60 degrees centigrade. Select the units here. It's already selected. Okay, you can already see centigrade by default, so we are happy. And pressure is 1.5. Sorry, 1. My God, 1.5, and you have to select atmospheres. Sorry, this is wrong. 1.5 atmosphere. Yeah. So everything looks fine to me. And then it says unknown flow rate. So what's the molar flow rate in this one? So we can write in terms of molar flow rate, because if you look at here, everything in terms of, if you look at the stoichiometric reaction, 1 mole of ethylene, 1 mole of chlorine, and 1 mole of ethylene dichloride. So it's better to maintain the molar flow rate. Yeah. So something like if you, it's easy to stick to the molar flow rate. If not, we have to convert everything into mass and mass back to mole. That will be nightmare. Yeah? So you will lose more hairs in the head. So it's better stick to molar units. So, and then if you look at here, we are going to perform 2 different chemical reactions: direct chlorination and oxychlorination. So instead of using 2 pump, we can use only 1 pump. So we can take ethylene at a massive flow rate, and then we can split, and then we can supply one for the direct chlorination, and then another stream we can connect it to the reactor where we are going to perform oxychlorination reaction. So let's do that. So I'm going to select something around 700 kilomoles per hour. Okay, so let's go back to, I'm going to put 700 kilomole per hour. So let's minimize this. So everything looks okay. So I will tell you quickly, because it's okay to like but you have to give some reasonable number, like 700 kilomoles per hour. So if you split them into half half, so it will be like a 350 kilomoles per hour goes to the direct chlorination step, 350 kilomoles goes to the oxychlorination step. So at the at the end of the day, you will get like so if the efficiency is equal to the stoichiometric efficiency, then you will get 1 mole of ethylene dichloride and 1 mole of ethylene dichloride here. So that should be equal to 350 kilomoles per hour of ethylene dichloride here, and 350 kilomoles per hour of ethylene dichloride here. That will be roughly equal to 700 kilomoles per hour. Yeah? And then so that should give some idea, like if you say 700 kilomole per hour, that should be equal to, you can convert it into how many kilomole hours per day. You can even convert it into how many kilomoles per year. I think I already did this calculation in the lecture too. So if not, so if you don't understand why these numbers, go and check the lecture too. And but anyway, once you finish the process flow sheet completely, like from reactant to the product, which is vinyl chloride monomer, I will show you like how, what will be the record level of flow rate here in order to produce, say, like how much, maybe like 1.5 million tons of 1.5 million tons of vinyl chloride monomer per year. So based on the annual production need rate, we can calculate, we can adjust the flow rate here. So I will show you once we finish the full process flow sheet. But for the beginning, let's select, okay, sorry, I think I did a mistake. Let's double click. So this is chlorine composition. So let's put it, the flow rate to be 350, 350, yes, 350 kilomoles per hour. And then, so we can also rename, just double click and then press the mouse on the one in the top, and then it won't show the cursor, it won't blink any cursor. You just put the mouse on the number one and then you can type CL2. That's it. And then you can close this. So you have one stream CL2. So we successfully added one input stream and then add one more. So what is this? So let's add ethylene. Ethylene composition. Ethylene is 1. If you put only 1 for ethylene, which means the remaining should be 0. This is a mole fraction. 1 mole of ethylene. So press OK. Now again, obviously it will say unknown temperature. We know that. So go to conditions, put the temperature to 60 degrees centigrade. All the fluid streams are maintained at the same temperature and pressure. Pressure is 1.5 atmosphere. Change the unit here. Okay. Unknown flow rate. So this time it should be 700 kilomoles per hour. So now it will be green color. Okay. And then you can even change the name to, just a double click on this stream, fluid stream, material stream, and then just put your mouse on one and then type there C2H4. If you want, you can type even ethylene. I prefer to use the formula. Close this. Now everything looks fine. And then let's add air. So instead of, look, we can add even hydrochloric acid. Hydrochloric acid. If you go back to the reaction, so we will add the hydrochloric acid. Obviously, if you have listened to the lecture 2, I said to you the whole purpose of oxychlorination reaction is to Mhm. Let me check the notes. Something is a bit puzzling to me. Yes. Anyway, during the pyrolysis step as well, we will have some hydrochloric acid. So when you use for direct chlorination, so you will get ethylene dichloride and then you pyrolyze them in order to produce your vinyl chloride monomer, which should release hydrochloric acid. So what we are going to do is we are going to recycle the hydrochloric acid and we will use it in oxychlorination reaction. But at the moment, we haven't developed the full process flow sheet, but we have to begin the process. So we are going to add a pseudo hydrochloric acid, but anyway, we will delete this particular stream once we build the full process flow sheet. So at the end of the day, we will get just reactants goes inside 1, 2, and then the only product that will come out of the process flow sheet will be vinyl chloride monomer. So we will do that at the, you will realize that once we finish developing the full process flow sheet. So let's go back to the Aspen HYSYS. I know I'm going a bit slow, but you won't learn if I go very fast, because you are learning Aspen HYSYS, not only the software, but you are also learning how to how to develop the full process flow sheet together with already gained theoretical knowledge about the process and together with already gained chemical engineering knowledge and the principles involved in all the unit operations and even the basic fluid properties and so on. So that's why I'm going a bit slow. Sorry for that. So the stream name what we're going to add now is hydrochloric acid. So this is a pseudo stream. So let's put the word pseudo. or maybe temporary if you want. Temporary. Temporary. Okay. And then we have to add the fluid composition. Hydrochloric acid is 1. So does the type 1 and then press enter and then press OK. So that should convert everything else to 0. Conditions again. Conditions again. So we need a hydrochloric acid at hydrochloric acid. So this one we are going to oxychlorination. We are going to perform at. Let's go back to the PowerPoint. Going to perform at 4 atmospheres and 225 degrees centigrade. Okay. So let's put that particular temperature 225 and 4 atmospheres. So let me check the notes. So this is how you are going to work as well. Yeah, you have to use your notes. If not, you are going to have really a hard time. So maybe let's put the same temperature and then we can raise the temperature. So that way you will learn how to add a heater and a compressor and so on. So let's put the temperature to stick to the 60 degrees centigrade. So let's assume everything is at same temperature and pressure 1.5 atmosphere. Change the units. Pay attention to the units. If not, it will become tough. Hydrochloric acid. So what should be the flow rate? So if you see here, ethylene fluoride we set to 350 because we are going to split the ethylene into two, one for direct chlorination and one for oxychlorination. So we have a flow rate of 700. If you split into half half, 350 and 350, and if you go back to the stoichiometry, you have here in oxychlorination reaction 1 mole of ethylene reacts with 2 moles of hydrochloric acid. So if we set 350 moles, 350 kilomole per hour, so it should be roughly twice. So let's put 350 multiplied by 2. Let's put 700, and then anyway we will change. I will tell why. So let's put molar flow rate of 700 kilomoles per hour. All are okay. So close this. Then finally we supply air. If you go back to, we need half a mole of oxygen. So let's supply air in excess. So let's put 1000 kilomole per hour. So add a fluid stream. Let's call it as air. Air should contain 79% of oxygen. Oh, sorry, 0.79. And then 21% of nitrogen. So press OK. We need only half a mole of oxygen. So 350 divided by 2, that is a very low number. So it's around 175, I think. So we can set the flow rate of roughly 1000. That should be more than enough. We're supplying oxygen, in fact, in excess. 1000 mole. Then temperature, let's put the same temperature, 60 degree. Pressure, let's put 1.5 at kilopascal. So everything looks fine. So we have the reactants for the. We can also just want, if you can click on the arrow and then we can move the location of the stream. So I hold the left mouse button and then I move left and right. So I hope this is okay for you. So, and then as I said, we are going to split the material stream. So how to split it into half? So then that's the location you have to go. So you press all here and then you drag the window. You will if you click on the if you put the mouse or your cursor on each of these symbols, it will say what is what. You have a mixture, you have a T splitter. So select the T splitter, place it somewhere on here. So okay, it has some by default it has some name for this particular operation, T100. That's okay. Just double click on it. So let's double click. Then there it will see what's your inlet. Inlet, I need to split ethylene, so I'm going to select ethylene. So it already connected, and then I need two outlets. I'm going to say call the first outlet as 1, and then I'm going to call the second outlet as 2. Yes, something is okay. This is okay. So we have we split it into 2, and it says unknown split. So it's asking like what's the ratio, the flow rate in each of those streams in 1 and 2. So for that we have to go to parameters. We can put the flow ratio 0.5, 50-50. Yeah. So 350 kilomoles per hour in the 1, 350 kilomoles per hour in the 2. If you want to know that, you can double click on 1, and then if you check the conditions and flow rate, you will see 350 here. So we are okay with that. So stream 1 goes to the direct chlorination, and stream 2 goes to the oxychlorination reaction. Okay. And then I said to you in the lecture 2, I said like in order to ensure complete conversion of ethylene in the direct chlorination reaction, I'm going to supply chlorine slightly in excess to that of stoichiometric amount. So if you go back here, so let's put it in the preview mode. So we have 1 mole, so 1 mole of ethylene, 1 mole of Cl2, 1 mole of ethylene dichloride. So I'm going to be supplied 350 kilomoles per hour of ethylene. So I'm going to supply one slightly in excess. Instead of 1 multiplied by 350 kilomole, I'm going to add slightly excess of Cl2 multiplied by 350. So what should be that value? Let me use my calculator. I don't know how to open the calculator in my phone. So that should be, I don't know how to use calculator in the phone. Let me try. 1.04 multiplied by 350. Okay, that's 364. 364. Yes. And then, so I'm going to supply 364 kilomole per hour of chlorine. So we are going to supply Cl2 in excess, and this will be our limiting reactant, ethylene. And then the same goes for here. We need to ensure complete conversion of ethylene to ethylene dichloride in the oxychlorination reaction. So we supplied 350 kilomole per hour of ethylene in the oxychlorination reaction. So twice this 350 kilomole per hour. Then we are going to supply hydrochloric acid in excess. So I selected some number of 1.08. So we're going to supply in excess, or we can even put 1.04. Let's see how it works. At the end, we can also check the efficiency of the overall process. Once you develop the full process flow sheet, I will explain you using the same PowerPoint. So that will be equal to 700 multiplied by 1.08. It will be equal to 756 kilomole per hour. The book which I used, they supplied 800. Yeah? So let's stick to the 756. Let's assume we supplied slightly in excess to that of the stoichiometric up. We supplied hydrochloric acid slightly in excess to that of the stoichiometric amount. So this is the required amount. stoichiometric quantity, and we supplied slightly in excess. It is 756 kilomoles per hour. Let's keep these things. Go back to Aspen HYSYS. So now I'm going to click on Cl2 and then change the flow rate to oh, I forgot what's the number. 364. Okay. Press close, and then we do the same for HCl temporary. So let's put what's the value? 756. 756. Okay. I think happy with this. Mhm. I don't know how long I'm recording this video. Check. Okay, it's already 1 hour and 23 minutes. So well, this is going to be a very long video. So what I'm going to do is let's focus on the direct chlorination part, and then I will stop recording, and then I will record again for the remaining part of the flow sheet. So let's go back to this presentation slide. So you see here, let's focus on direct chlorination. So let's use a continuous stir tank reactor to mix this and assume you already have a catalyst loaded inside, and then you're going to get this product out. Okay. So how to do that? It's very simple. So we have to, let's mix both of the fluid stream first. Mhm. Or maybe I can, let's do one thing. Let's maintain everything at room temperature, 25 degrees centigrade. Just changing the temperature, everything to room temperature so that I can show you how to add a heater and so on. So the fluid streams are maintained at 25 degrees centigrade. So let's mix both of the reactants. So this is our 350 kilomoles per hour of ethylene, and so roughly 364 kilomoles per hour of chlorine. So we have to mix these two. Let's select a mixture. It's here. If you put the cursor, it will say mixture. Just to drag and drop here. Just to double click. So what are the things we want to, what are the fluid streams that we want to mix? We want to mix one that contains ethylene. And then we want to mix chlorine as well, Cl2. Okay. And then outlet, let's give a number 3. We already used the number 1, 2, and 3. So let's put the number 3. Okay, it's already mixed. So if you see the molar flow rate here, 710 kilomoles per hour, and then temperature is 25, pressure is 152 kilopascals. And if you go back to our PowerPoint, you can see here we need to, the pressure should be 1.5 atmosphere, which is already maintained at 1.5 atmosphere, but we need to raise the stream to 60 degrees centigrade because we are performing this reaction at 60 degrees centigrade. So let's do that. So So how to do that? We have to add a heater to raise the temperature of the stream. So let's click. If you go to the, it's called as a palette. So click on the palette and then you can see heater. Just click and then you place it on this window here, the working window. Double click. So what is that? Inlet stream is 3. Outlet stream is, let's call it as a 4. Just enter it. So records an energy stream. Let's call it as a QE1 energy stream name. Put 1. Unknown delta P. Let's say the pressure drop is 0. Parameters. Let's put 0. Unknown duty. Okay, this one we don't have to calculate. Let's close this one. It will calculate automatically for us. Let's close this. And we can fix the temperature so it will calculate the duty automatically. So double click on the fluid stream. We want the stream to be maintained at 60 degrees centigrade. So let's click the temperature to 60. And that's it. So it automatically calculated the duty. So click here, or if you even if you put the cursor, it will tell the conditions. 60 degrees centigrade, 1.5 kilopar atmospheres. So this is the perfect condition. And then we can add a continuous stir tank reactor where we are going to mix these things, and then we can going to take the product out. It's very funny in Aspen HYSYS, like you cannot take two streams and then add a CSTR and then maintain the temperature inside the CSTR. No, we have to, if you're performing some reaction, say at 800 degrees centigrade, you have to make sure the stream which enters that particular unit operation is at 800 degree centigrade. That's how Aspen HYSYS works. So we cannot add a reactor and then we can define, okay, this reactor is maintained at 800 degrees centigrade. No, you can't mention that. So all we need to do is add a CSTR and then just make sure that your fluid stream enters at the right conditions, like right temperature and pressure that should be maintained inside the main unit, which is the mixing tank. So we are just assuming we can perform this direct chlorination reaction. So we're going to add these two of these things. These are both are in gas phase. Normally in industries they use a gas liquid reactor. So, but here we are going to model it like a continuous stir tank reactor. So these two gas streams are going to enter, and then we're going to get the liquid ethylene dichloride product because the this particular condition, 60 degrees centigrade and 1.5 atmosphere, is below the boiling point of ethylene dichloride, which means we will have only liquid. So let's add a continuous stir tank reactor. Where is that? You can click reactor. Okay, it's here. Continuously stir the tank reactor. Click here and then drag and drop on the window. So just double click. It will ask which stream goes inside. So I'm going to say stream 4 goes inside. Okay, happy with that. And then we can call it is something like a vent. There is some gaseous emissions because we are dealing with the hydrocarbons. Obviously, there should be some gas released. So if some unconverted reactants, it will be still in gaseous phase. So we need some vent. And then liquid outlet is let's call it let's give some number 1, 2, 3, 4. We used until number 4, I think. So let's give the number 5. So it says so once you added these values, so it's asking requires a reaction set. So and you should keep in your mind, you should have some chemical engineering knowledge and some idea about the fluid properties, because we are dealing with the hydrocarbons, ethylene, and obviously it's going to release some vapor. So probably we need to add some vent. If the conversion is not completely full, then you might have some gas in the top of the reactor. Yeah? So we need some vent to release those gases and so on. And obviously this is number 5 is something like a product out from the continuous stir tank reactor. So these are something only chemical engineers can think and do it. Then we have to add a reaction set. So we are dealing with a direct chlorination, and if you remember in the reactions, we already added reaction 1 for the to describe the direct chlorination reaction. So just select reactions and then press reaction set. It's set 1. Under set 1, we have 3 reactions. We have to select reaction 1. So perfect. And then it says volume not specified. Obviously, we didn't specify yet. So it's going to highlight that error. So this is one advantage with Aspen HYSYS. So it will tell us what should we do, what should we think next year. So we have to define the volume, and still we are not sure that about the percentage conversion. Yeah? So So still we have to dig into the literature for the values. Like if you go into the literature, you will find some information like, okay, your residence time should be blah 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 hours in order to ensure complete conversion of your reactants into products. Okay, so if that's the case, let's specify the volume. How to specify that? Where is the parameters? Going to specify. Check my notes because I'm getting a bit confused with these things. Mhm, mhm. I think it's okay, fine. Volume. Let's put liquid volume is 50 percentage. Reactions is set one. Rating. I'm going to put liquid volume is 3000. Oh, sorry, here. Three, I'm going to fix to the value of 3000 meter cube, liquid volume of 50 percentage, or you can even put 80 percentage. Something is happening. I couldn't type in the keyboard. Okay, 880 percentages. Okay, it's calculating something and then it came up with some conclusion. So I think everything looks fine anyway. So this is some temporary volume that we are entering, and we are assuming 80 percentage is the liquid volume. It's okay. And then connections are fine. Everything looks fine. Reaction, we correctly entered reaction 1. It already converged. You will get some yellow, and then after some time it will change to green. Yeah? It will do some calculations. So it will take some time. I think everything looks okay to me. I think let's close this. So you can click on 5 and then you can put it a bit down to look clear. So I think this, if you look at stream 5, and if you go to composition, mhm, mhm, I think we entered the rate of reaction, everything correct. Maybe volume is too low, I think. Let's double click. We supply a massive flow rate. I think change the volume parameters. Let's put to 30,000. Volume not specified. I think we already specified. Okay. Okay, my computer is very slow. That's the problem. It's not the Aspen HYSYS. Parameters looks fine. Reaction stoichiometry looks fine. -1, -1, +1 C2Cl2. Okay. Still, I don't see any product in the composition. Okay, let's continue. Mhm. And then we need to specify the residence time. This is something really important. So how to do the residence time? So if you go into the literature, I think I said it in the lecture 2, I think it's we need to maintain a residence time should be equal to let me check my notes. The residence time should be equal to 2.240, yeah, in order to ensure complete conversion of your reactants into product, at least 99% conversion of reactants into product. So let's double click on this, not this one, sorry. So if you see here, if you go to the model palette, if you press all, and then you can, if you come down, you will see here spreadsheet. Click the spreadsheet, and then you place it below the CSTR, or you can place it anywhere in the window, but anyway, we are going to work something related to the CSTR tank. So just open the spreadsheet and then go to parameters. Sorry, go to spreadsheet, sorry. Go to spreadsheet, and then let's type it in the top. CSTR direct chlorination. This is for our reference, nothing else. And then let's say like actual flow rate or flow rate. Flow rate in to CSTR, and then volume of CSTR, and then residence time CSTR. Yeah? So this is a flow rate of flow rate in CSTR. So just right click, add import variables. So what is the flow rate that what's the flow rate of the stream that enters the CSTR? That's something that we need to define. So that's I don't know which number goes inside. Okay, stream 4. Right click, add import variables. Stream 4, this is the stream that goes into the CSTR. So select stream 4, and then what we have to select is a molar flow rate. So we can select here molar flow, then molar flow. Just click done. So 714 kilomoles per hour. That's the molar flow rate of the streams that go into the CSTR tank. And the volume of CSTR, what is that? Just right click, add import variable, select CSTR unit, and then select, you can select here volume. It should be somewhere in the bottom. Tank volume, I think. Select the tank volume and then press enter. Press done. Yes. So we can calculate this residence time. Residence time is nothing but volume divided by the flow rate. So residence time is divided by. So let's say this is okay. This is volume divided by flow rate. So that should be equal to B3. B3 is this cell divided by B2 is this cell, 714. B2. So 42.20. So this value, so if you check in the literature, we have to maintain a residence time of 2.240. So that's the main objective. So how to do that is like, so once we built the spreadsheet, now we know how to build a spreadsheet. This is something you learned through this exercise. So let's close this one. So why we are adding this spreadsheet is to, because we are going to adjust the residence time, and then we are going to adjust the volume so that we know the flow rate, and then we are going to adjust the residence time so that in order to ensure complete conversion. And how to adjust the residence time? We have to adjust the residence time to 2.240, or maybe no, it should be 2.5814. That's the main objective. So let's click. You go to the model palette, and then you have to search for something called as agile. You will see something like a spanner. So click on that one, place it somewhere here next to the spreadsheet, and then just a double click. Just a double click. So which is the object that we are going to adjust? So we are going to adjust the CSTR tank. Select variable. So select CSTR1. Then we are going to adjust the tank volume. We're going to adjust the tank volume. Select. And then what we are going to change, select our target variable. So we are going to change the tank volume in order to achieve the residence time equal to 2.5814. So that's why we are going to adjust. We are going to modify the volume of the CSTR because the flow rate is fixed. So we can change the volume of CSTR that will ensure the residence time is exactly equal to 2.5814. So that 2.5814 comes from the literature. So what we need to change is we have to select a spreadsheet. In B4, we calculated the cell B4, we have the residence time. So select B4 and then press select. And then what's the specified target value? That should be equal to 2.5814. I think this is, sorry, 2.5814. Then press start. Sorry, 5814. Still solving, I think. Minimum possible temperature. I think it's still solving, I think. It's giving some warning. Spreadsheet. Okay, still calculating. We maintain the temperature of 60 degrees centigrade, 1.5 atmosphere. Friction stoichiometry is good, I think. still adjusting the volume to eventually it should solve the. Mhm. Let's wait. I have no problems in waiting until it solves the. Because I already tried this exercise myself before starting the lecture and everything worked fine. You shouldn't encounter any problem. If there is some problem, we can even delete the CSTR and then we can start again one more time. Anyway, it's not going to make any big difference, I think. Do you wish to continue another 10 iterations? Yes, I like to continue. I think it's doing something funny, which is not funny. This is the boring part. If there is an error, I don't like it, honestly. So if you are trying, try to be patient and then see what happens. You didn't do any mistake, that's for sure. Something is not happening. It's still trying to solve. Probably we started from a very massive volume. I don't know. Mhm, mhm. It's trying to solve. Probably I will try to edit once it's converged. Then I will try to edit the video so that it will save you some time. So I'm just capturing the screen, whatever it's happening, the number of messages, series of messages which is appearing on the screen, so that you will get some idea. Something is running behind. So what at the moment we are trying to do is we're trying to fix the residence time around the 2.5814. This is taken from the literature. Hmm, I don't know what's the problem. Spreadsheet, tank volume, select variable. So let's stop this one. Reached iteration, limit without converge. Let's put reset. Let's close it and then let's check the design, reactions, details. Just setting the liquid volume to 100. Yes, okay, it's converged for some reason. Okay, let's close this. It's like, let's adjust. I'm going to close this. Let's repeat this process of creating this adjust. Let's delete adjust value. Spreadsheet, close the CSTR, the volume, say 3000 meter cube, green, 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 all fine. And then add adjust tool again. So we are going to adjust the tank volume, CSTR tank volume, CSTR tank volume, select objective, select variable, go to spreadsheet, B4, 2.5814. Yes. Oh, it's converged. Okay. Okay. So better select the, if you put the liquid volume to 100 percentage here, then when you are adjusting this one, you can select tank volume, yeah? Or if not, yeah, so better select 100 percentage and then press this tank volume. I think if not, if you have 80 percentage or 50 percentage of liquid, then you can select, just select the, no, it should be tank volume. Yes. I just started with the 3000 cubic meter, cubic meter, sorry. So starting number, and then use this adjust tool, and in order to make the residence time is 2.5814. I think I'm happy with what happened so far. And if you click the spreadsheet now, you will see the residence time is something that we fixed, 2.5814, and the record volume is 1843 cubic meter. And then for the flow rate, corresponding flow rate of 714 kilomoles per hour. So this is perfect, I think. Everything looks fine to me. Mhm. So what I will do is I will take a pause now, and then let's continue with the remaining stuffs in the next lecture. So thanks for listening.